Hello and welcome to Year 11 Chemistry, Paper 2 Revision, Topic 7, Organic Chemistry. Now this is the first of a two-part video series on organic chemistry. Why two videos? Well, if you take a look at the topic list, on the combined it's very short, it's only 4 chapters, but if you're doing triple, it's much longer. So I've decided to split it into two videos, one for the combined students and an extra video for the higher. But that doesn't mean that the higher students ignore this video. You still need to get the basics in green as well. So I'm going to go through this. This will be a nice, short, sharp video. So what is crude oil, okay? What is this magical substance that has made the modern world? Here's a picture of the Industrial Revolution. We started using it around 150 years ago. Although we're nearly running out, so it's a non-renewable fuel, but it has been the basis of the modern world, so it's not all bad, okay? So firstly, the formation of crude oil, is it formed? Crude oil is formed from the microscopic remains of little tiny sea creatures. They're kind of called plankton, and over millions and billions of years, they sunk to the ocean floor. Maybe they went to animal heaven, but their bodies sunk to the ocean floor, and they eventually got crushed by great pressure and mud into oil and natural gas that we now use as crude oil. Here's another example, and this takes millions, if not billions of years, so it takes a long lot of time. Okay, crude oil is a mixture of different hydrocarbon molecules, and as you can see, they have different lengths. This is going to be very important. But firstly, you need to know what a hydrocarbon is. A substance made from carbon and hydrogen only. The key word is only. As you can see, there's only carbon and hydrogen here, nothing else. So alkanes. What is an alkane? It's part of what we call a homologous series, and this will be a lot more clearly explained when you see the diagrams. But an alkane, all I want you to know for now is that the end in ANE, and they are hydrocarbons. So homologous series, it shows a gradual gradation in physical properties. They just basically get a bit longer. That's all it means, okay? So they just meet one carbon atom, two carbon atoms, 20 carbon atoms. They just get longer and longer. That's all you really need to know. Okay? So you need to know for your course the first 4 alkanes. They are methane with 1 carbon atom, ethane 2, propane 3, and butane has 4. Okay, you need to know what the general formula is, and it's CnH2n plus 2. Well, let's take a look where this actually comes from. Well, the Cn comes from the number of carbon atoms. In this case, it's 4. The hydrogen, as you can see, there's 4 hydrogens above and 4 below. That's where 2n comes, so that's 8. And at either end in green, there's 1. That's where the plus 2 comes from. So the general formula here will be C4H10. So here's some questions you might get asked. Crude oil is formed by the decomposition of, and alkanes or hydrocarbons. What's the third one? Well, you could say biomass, plankton, microscopic plants and animals. That's what I just showed you in the diagram. And the third one is propane, as you can see there. Okay, so this next question, the diagram shows the structure of a molecule of methane. Write down everything this tells you about the methane molecule. Now, any one from 3, it's got 1 carbon atom, 4 hydrogen atoms, it's a hydrocarbon. Saturated, you won't know what that means yet till I start talking about alkenes, but it means there's no double bond, and so on. Why does it say any 3? Well, it was actually one of those where they want quality of written communication, so they want you to spell everything correctly as well for the extra mark. Describe how crude oil is formed, plankton or marine animals. Ignore plants. Plants were not evolved at this stage. It was microscopic organisms buried in mud or compressed under rock over millions of years. Now, you might want to look at this, okay? The properties of hydrocarbons, of which there are 3 you must be able to discuss, and it's all based on the chain length, okay? How long the carbon chain is. Is it 1? Is it 3 carbons? Is it 70 carbons? You're going to see what I mean now. Boiling points. The shorter the hydrocarbon chain, the lower the boiling point. The longer the hydrocarbon chain, the higher the boiling point. This is because the longer chain length, the stronger the weaker the intermolecular forces between them, the higher the boiling point. And as you can see here, methane has a really low boiling point, minus 162. Ethane, minus 89, minus 42. Butane, bang on 0. As you can see, they increase with the chain length because there are stronger, weak intermolecular forces. You're going to see this is very important when we come to separating them out in fractional distillation in our next little part. Next, flammability, how easily they burn. The shorter the hydrocarbon chain, the more flammable it is. The longer the chain length, the less flammable it is. Why? This is because the longer the chain length, the harder it is for oxygen to react with the carbon atoms in a combustion reaction. The oxygen just can't get in at the carbon when the chains are really long. That means methane, which is really small, the oxygen can access it easily in a combustion reaction, making carbon dioxide and water. Whereas in road tar, which is 70 plus carbon atoms, if I throw a match on the road, it ain't going on fire, it's not flammable, because the oxygen can't get at the carbon atoms when the chains are that long. Next, viscosity. It's a fancy name for how runny or how sticky a substance is. Water would have a very low viscosity because it's runny. Jam would have a high viscosity because it's sticky. And as long as you have a mental image of that, you know what viscosity means. The shorter the hydrocarbon chain, the less viscous it is. The longer the chain, the more viscous it is, and it's again to do with the weak intermolecular forces. The longer the chain, the stronger the weak intermolecular forces, the more viscous or sticky the molecules become. Please use the term viscous. Sticky is everyday language. Now, petrols, short chains, low viscosity. Bitumen, long chain, high viscosity. You can see how sticky it looks in that picture there. Now, here are some exam questions. Compare the structure and properties of methane and hexene for 6 marks. 6 marks. The most important word in any 6-mark question is and, because you naturally split it into 3 marks. 3 marks for structure and 3 marks for properties. Well, here's your 3 marks for structure. Methane has 4, hexene has 14 hydrogen atoms. Both contain CH bonds. Students aren't too good on similarities. Only hexene has CC because it's got more than one carbon atom. Both are hydrocarbons and hexene is larger. Very, very easy. Properties, hexene will obviously have a higher melting point and boiling point because it's got stronger weak intermolecular forces. Methane is a gas, hexane is a liquid, and then viscosity. Hexane will be more viscous and both are flammable. And at the end, they chuck in neither conduct electricity. Not something I would have put down, but it is on the marking scheme. Now you need to know what complete combustion is. Complete combustion is when a fuel has enough oxygen to react completely, okay? When the carbon atoms can be fully oxidized to carbon dioxide. And you do that in your kitchen all the time. It's fairly safe. Where you get really worried about carbon monoxide, that's toxic, but carbon dioxide, while it's not great for the earth, it's a greenhouse gas, traps the earth heat, causing global warming. It's not the worst either, okay? Okay. Now, testing for the products of complete combustion, you must know how to test for carbon dioxide. You bubble it through lime water, it will turn cloudy. And just in case, the test for water is you've made copper sulfate and it's blue, but copper sulfate should actually be white. What you've made is hydrated copper sulfate. If you dry out copper sulfate, add water, it turns back blue. Now, next we're on to balancing equations. I know this is chemistry topic 1, but they do like asking with combustion reactions, and I did use this example, the combustion of propane, so I'll just go through it quickly again. This is an unbalanced equation, and it's trial and error. First you start with the carbons, they match. Hydrogens don't match, stick a 4 in front of the water, they match. Finally, stick a 5 in front of the oxygen on the left, and you've got a balanced chemical equation. The reason I've rushed through this is if you watch my chemistry paper 1 video, I've done the same thing. So, but just be aware of time, because it's a 3-mark question. They'll give you 1 for the reactants, 1 for the products. But balancing is only worth 1 mark, so don't waste too much time on it. Now we're next on to the second part, the fractional distillation of crude oil. Why do we do this? Crude oil is a mixture of different hydrocarbons We have to separate them out in order for them to be useful. You can't put diesel into a petrol car or vice versa. You can't put petrol into a plane. You can't tar a road with diesel, okay? You have to separate these things out unless you want your car engine looking like this, okay? So how do we separate out these different fractions, okay? What you do is you use a thing called fractional distillation, and it's based on the point that the different fractions have different boiling points. The longer chains will have higher boiling points, the shorter chains will have lower boiling points. And here's what it's called, a fractionating column. And as you can see, the longer chains are near the bottom and the shorter chains are near the top. It's hot near the bottom and cooler near the top. I'm going to talk through this process in extreme detail in a moment. Here's another example. Kerosene for airplanes, diesel for lorries, slower burning fuels for ships, shorter burning fuels for cars. And now they might ask you to compare the properties of two different fractions. I'm going to talk about the actual process in a moment, but quickly, let's compare petrol with diesel. Petrol is above diesel, so it will have a lower boiling point because it has a shorter chain length. It'll be less viscous because it has a shorter chain length. And finally, petrol will be more flammable than diesel as it has a shorter chain length. Well, let me talk through the fractional distillation of crude oil in detail now, because you do need to know it for your exam. So pay close attention here. The crude oil is completely vaporized by a heater and pumped into a fractionating column. Quickly, why is that done? Well, if I didn't vaporize it with the heater at the left, it will just all flow out the bottom where the bitumen is and not be separated at all. So I must vaporize it to a gas so it travels up through the column. Now, the column is hottest at the bottom and coldest at the top. The different fractions have different boiling points due to their different chain lengths. Therefore, they condense out of the fractionating column at different points, separating them. That is the fractional distillation of crude oil, and they love asking that question. So here's another question from a real life. Complete the formula of nonane. I know it's an alkane, so it's going to be double the carbon atoms, that's 18, and then you add 2 on the end, it's 20. They might ask you what's the boiling point. I think 95 would be a reasonable guess there, but they'll generally accept any number in between the two within reason. Nonane will condense lower in a fractionating column. Explain, and you should refer to the temperature gradient. Well, let's have a look here. Okay, nonane will have a higher boiling point, so we'll condense where the column has a higher temperature, and the higher temperature is at the lower point of the fractionating column near the bottom. Describe how crude oil is separated into fractions by fractional distillation. 4 marks. Exactly what I said. It's heated, it's vaporized, and they will condense at different points because the fractions have different boiling points. I don't know what question C was, but I presume it was what was the general formula of alkanes. Next, we're on to cracking. What is cracking? Cracking is the thermal decomposition of long or large alkanes into short or small alkanes and alkenes. I'll explain what alkenes are in a moment, but just know how you use cracking. It uses high temperature and a catalyst. So some students say heat, but the market scheme doesn't generally reward heat, so it does say high temperature. Why? There is a much higher demand for short alkanes as they are consumed every day as fuels. And secondly, alkenes are used to make plastics, and the plastic industry is worth billions. So here are alkenes. What's the difference between alkanes and alkenes? Alkanes don't have a carbon-carbon double bond. Alkenes do have a carbon-carbon double bond. Unsaturated means it has a carbon-carbon double bond. Saturated means it doesn't have a carbon-carbon double bond. You may be familiar with the term saturated fat and unsaturated fat. Saturated fat is much worse for you because without a carbon-carbon double bond, it's much harder for your body to break down and would clog your arteries. So the test for alkanes versus alkenes, all students need to know this. You add bromine water, and bromine is an orange color, and it's a test for the double bond. If there are no double bonds, it's an alkane and it will stay orange. If there are double bonds, it will become decolorized. The color changes from orange to colorless. Here, for the triple higher students, you do need to know what actually happens. What you'd say is this, is the bromine adds across the carbon-carbon double bond, breaking it in an addition reaction to form 1,2-dibromoethane. That's for the triple students only. That's why it actually does become colorless. Alkanes, I generally think, are used as fuels, and alkenes, I generally think, as being used for plastics. Now, crude oil naturally has a much higher proportion of longer chain hydrocarbon molecules than the more useful short ones. So what are we going to do about that? How are we going to make our money? Well, this is where cracking comes in. Okay, cracking makes supply meet demand. As you can see on the far right, there's far more fuel oil and bitumen than you actually need. Once I tar a road, I'm not going to come back and tar the same road the next day. It doesn't make any sense. Where you take a look at petrol on the left, petrol is consumed every day as a fuel. There's a way higher demand for petrol than there is supply. After cracking, it makes supply meet demand, and that's where you get the money. Okay, so what is cracking? And it's the thermal decomposition of long-chain alkanes into shorter chain alkanes and alkenes using heat and a catalyst. Now, in reality, you'd be doing it with carbon molecules, 50, 60, 70 long. I can't draw that. No one can draw that. So we're just going to show you septane, C7. And as you can see, it must always add up. 7 minus 2 is equal to 5. 16 minus 4 is equal to 12. That's the law of conservation of mass. Here's the longest one I could squeeze to draw, but again, the reactant equal the products. Here's an example of diesel being cracked into petrol, more useful, paraffin, and ethene for plastics. And another example of kerosene being cracked into octane and ethene. Steam cracking is where steam used a very high temperature as a thermal decomposition, and again, a catalyst. So, again, more cracking, more cracking, more cracking. And you can demonstrate it in a lab. If you get some paraffin and porcelain as a catalyst, you will get bubbles of ethene gas that you can then test with bromine water. So here are some examples here. This is just a conservation of mass. 90 minus 35 is 55. And if you take a look, 8 minus 2 is 6. And 18 minus 4 is 14. Or you need to be able to work backwards by addition. 6 plus 10, 6 plus 22 is 28, and then 3 plus 10 is 13, and the masses add to 180. Real life exam questions: explain the advantage of cracking hydrocarbons. Give one example from the table. If they tell you to do that, you must. Here's what I would go with. You break large molecules into small to satisfy demand, and the example I picked was there's a 9% supply of petrol, but a 23% demand. Cracking will solve that problem. You also need to remember your papers are synoptic, so they can ask you about moles, even though it's more on paper 1. Calculate the number of moles of ethene. Well, I've had to convert from kilograms to grams, and I get 1800 moles. In the next question, however, they want my answer in kilograms, so I don't have to convert from kilograms, so you do it like this. As you can see, it's a 1 to 3 ratio, okay, working backwards. So I divide by 3, so I need 0.6 moles of C21H24, which weighs 296, and there you get your answer. Here's another example. Large hydrocarbon molecules can be cracked. Give 2 conditions. High temperature and a catalyst are the ones I would go for. It says ignore heat though, and I don't like that because a lot of students would write that. That's where precision comes in. You need to hit that marking scheme, okay? And finally, okay, here's another example. Balance the equation, easy, and describe the differences between cracking and distillation. Just a random throw question that you mightn't have been taught. Cracking involves a catalyst, distillation does not. And distillation does not involve a chemical change. You are just separating on the physical boiling points, but cracking does. That is a more difficult question, but it's only worth 2 marks and I wouldn't lose too much sleep over it. So that is the intro to organic chemistry, son. Done. Combined students, that's it for you. Triple students, I will see you for our next video where we go real deep on our alcohols or carboxylic acids or polyesters. I can't wait. Okay, I will see you then. All the best.